So today we're going to continue to talk about acid-base equilibria. We're going to move on from our weak acids and we're going to talk about weak bases. And so just as a weak acid would have an acid ionization constant or a Ka value, weak bases are going to have a base ionization constant associated with them or a Kb value. But before we start to talk about weak bases, I'd like to take a minute to just discuss strong bases. Now, and how we can use a solubility chart to help us identify if a base is strong. So I'm hoping that you remember from grade 10 science that the hydroxide ion is typically associated with solutions that are alkaline or basic. And so anytime we look at a hydroxide compound, a hydroxide compound that is highly soluble, what we're looking at is a solution where there's 100% dissociation happening. And so if that's the case, then we have, the number of particles that we start with will be the number of particles that dissociate and produce hydroxide ions in solution. So let's see how we do that. So if we were to look at our hydroxide anion on our solubility chart, we can see that there are a number of them that are highly soluble. And so, for instance, here we have all of our group 1 hydroxide compounds, our ammonium, strontium, barium, and so on. So for instance, if I were to say sodium hydroxide is a strong base because I know that that's a reaction that will go to completion. An aqueous solution of sodium hydroxide will liberate all of its sodium ions and all of its hydroxide ions. So that if I had 100 particles of sodium hydroxide, that would liberate 100 hydroxide ions. So there's a stoichiometric equivalency there. And so, how is that helpful to me? It's helpful because I don't need to use Kb values for that. What that is telling me is that whatever I start with as a concentration of sodium hydroxide will be my hydroxide ion concentration once this reaction happens. And that's not true when we look at weak bases. So if we're seeking out the pH or the pOH of a weak base, we can't use the original base's concentration because the concentration of hydroxide that ends up in solution isn't necessarily the same as the concentration of that base that we started with. So let's look at one way that we can represent a weak base's equilibrium law. So you'll see here that I have what I'm describing as my weak Bronsted base. In this case, I'm choosing a neutral particle. I'm going to show you another option here, though, in a minute. Now, you'll remember that weak bases are proton acceptors, and they're going to accept it from whatever other molecule that they happen to be in reaction with. In this case, I've said water. So water is going to act as an acid in this case and donate its proton to my weak Bronsted base. And in so doing, what I end up with is this conjugate acid, which I'm calling BH plus in this case. When water liberates that proton, it becomes hydroxide. And it's this hydroxide here that's going to result in the solution becoming alkaline. Okay, so in this case, as I've written this, the corresponding Kb expression would be the concentration of my BH plus, that conjugate acid, times the concentration of hydroxide ion, divided by the concentration of my weak Bronsted base. I just want to show you an alternative to this. So I'm just going to do a couple of things to erase and start over. So let's just say, for instance, instead, that I started off with, often we see that our Bronsted bases can be anion. So let's just say that this were, for instance, negatively charged. Then what I would see is that I would still see that same proton donation, except that I would just not have that positively charged conjugate acid in the end. My Kb expression would be the same, just with that charge gone, right? So BH times the concentration of OH minus divided by the concentration of B minus. So those are, those essentially can represent the same thing. Okay, let's take a look at some problems we might see involving Kb and weak bases. So the typical example we see is one where they're asking us for the KB value to be calculated, such as this. So let's take a look. It reads, methylamine is one of many substances that gives herring brine its pungent odor. Amines are often really smelly. So a 0.1 mole per liter methylamine solution, which is a weak base, the pH is 11.80, and so that pH there is telling you that it's a base and not an acid. And the fact that they're asking us for the KB of it leads me to suspect that it's weak. So we're going to go about things in that manner. So I would always start out with taking a look at an ice box of some description. So that's actually where I'm going to start, is just creating an ice box. And I'd like you to pause the video to try and complete the rest of this equation. CH3, NH2. How do I finish that? So this is what you want to do. You want to make sure that you're writing out the particular base, CH3NH2. You're going to react it with water. You're going to hydrolyze it. And in so doing, what we're seeing here is we're seeing this methylamine act as a base. So bases are proton acceptors. It's going to accept a proton from water. You may be concerned about where you're putting in that proton. I'm less worried about that. You can sort of, it's not going to have any effect on the math that we do. So you can either put it at the start of the compound or at the end. I'm going to go CH3NH3 plus OH minus. Okay, so I didn't talk about it, probably should have. Remember, water is in the liquid state, and so its concentration is unchanging. So we're not going to see it participate in the equilibrium law for this weak base. I'm going to fill in my 0.100 moles per liter methylamine. At the start of this, no ionization has happened, so my product concentrations are 0. I'm going to decrease my amount of methylamine over the course of this, giving me an equilibrium expression that looks like that, 0.100 minus X. Now my ion concentrations of these products are going to only increase because of the starting position of the equilibrium, giving me values of X and X. Now, what I want to focus in on right now is this piece, which is that they are actually giving me the pH is 11.80. And so the pH can give me some really important information about my hydroxide ion concentration. That's, so that's really where I want to start, is how can I use that pH to fill in some information about my hydroxide ion concentration. So a very common mistake that I see is students think that they can calculate the hydroxide ion concentration directly from pH. And you can't do that. So let me explain why not. The pH, and I'm going to call this step number 2, by the way. Let's call this step number 2. Which is that I'm going to calculate, I'm going to use that pH to figure out my pOH. Remember that pH, just to start off here, that pH is equal to the negative log of my hydronium ion concentration. So I can't use the pH to find out my hydroxide ion concentration because that's just, the formula that I've written here doesn't really work for that. But there's another formula that I know that can relate pH to something called pOH. And so I'm just going to start over here. I know that pH plus pOH equal 14. And so if I substitute in my known pH of 11.80, that will allow me to solve for my pOH. So I end up with a pOH value here of 2.2. So at this point, I want to create another slide so that we can sort of clean this up a little bit and then still have this slide to look at. And so I've taken a little screenshot of where we left off. I'm going to call this step 3. And so remember that the question asked me for the Kb value of methylamine. And so what have I figured out so far? Well, so far I know that the POH was 2.2. And so that will allow me to figure out my OH concentration, because the value of X here is going to be equal to my hydroxide ion concentration. So my hydroxide ion concentration is equal to 10 to the negative POH. So substituting in my POH of 2.2, I'm going to get a value of 6.3 times 10 to the negative 3 moles per liter. And you'll remember that that's actually what X is, right? So X represents my hydroxide ion concentration. So now I'm in a position to be able to calculate Kb because I have a value for X. So that, now I'm ready to finish off. So I'm going to call this step 4. And I'm going to write out my Kb expression here. So Kb is equal to the concentration of this particular, my conjugate acid, times my hydroxide ion concentration divided by the concentration of methylamine. So I have X times X over 0.100 minus X. And I'm just going to substitute in the values that I have here for X. So 6.3 times 10 to the negative 3 squared over 0.100 minus 6.3 times 10 to the negative 3. And that's going to give me a value for Kb. And I'm hoping that we all arrived at the same number. I got 4.2 times 10 to the negative 4, and that is my value. I want you to take a look at the next question and give it a try on your own, pausing the video and then resuming when you're ready. Here it is. It says calculate the pH of a 0.20 mole per liter solution of ammonia. So go with this as far as you can and then resume the video when you're ready to take it up. Okay. I'm going to break this down into steps. I tend to like to start by writing out my reaction equation. And my reaction equation in this case is ammonia plus water goes to make, again, my ammonia is acting as a base, so it's going to accept a proton from water, forming NH+, the ammonium ion, and liberating some hydroxide. And that's where my alkaline solution is going to come from. I'm going to set this up as an ice box. And I'm going to ignore water because, of course, everything else is in the aqueous state. Water is in the liquid state with an unchanging concentration. So ammonia is starting out with, I'm starting out with a 0.20 mole per liter solution of ammonia. And no ions have been produced at the onset of this. I know that over time, because I have no dissociation at the onset, that my ammonia concentration is going to decrease, giving me the expression 0.20 minus X at equilibrium. My ion concentrations can only increase. And so I'm going to represent that with the variable X in this case. And so now I'm just about all set. Now, you may have gotten to this point and gotten stuck, because it seems as though there's not a lot of information given in this question. Now remember the topic. The topic of this lesson is base ionization constants. So what I'm really hoping you knew to do was to go and take a look at your textbook in the back of it to the section entitled Weak Bases and look up ammonia. Ammonia is a weak base with a Kb value of 1.8 times 10 to the negative 5. So that's helpful, and I'm going to utilize that in my solution. So I'm just going to write that out. 1.8, so Kb for ammonia is 1.8 times 10 to the negative 5. So just remember that you have that reference piece in order to help you through this question. So I ran out of real estate, so I created a new slide and just wrote all the steps we've done so far. So I'm just going to carry on from there. The third step here is going to be to go ahead and write out the Kb expression for this. So I know that Kb in this case is going to be equal to the concentration of my ammonium times the concentration of my hydroxide ions divided by the concentration of my ammonia. And I'm just going to substitute all my known values and expressions into this equilibrium law. So I have x times x, which would give me x squared, divided by 0.20 minus x. And so now I have to kind of make a decision. I want to say, well, is this Kb value at an order that would make it, this value of x here, this decrease, small enough that it would be probably insignificant? And the answer is that considering significant digits, that is likely to happen. And so I'm going to go ahead and make the decision to just simplify my math by getting rid of that x value. And then now I have a much simpler equation to solve. So I'm going to go ahead and do that. So the resulting, I'm just going to move this up here. The resulting equation that I would have would be 1.8 times 10 to the negative 5 times 0.20 is equal to x squared. That is an easy peasy equation to solve by taking the product and then the root of that scenario. I'm just going to go ahead and do that. You do that yourselves as well. I am getting a value of 1.9 times 10 to the negative 3 moles per liter. And so let's just kind of examine that, right? So when I look at this, I'm just going to focus on this little bit part of the equation. And so the equation that I have here is, for my concentration ammonia would be 0.20 minus 1.9 times 10 to the negative 3. So when I do that, if I were to round to 2 sig figs as I should, I'm still getting 0.20, which means that was a valid exercise. I was okay to do that. But I'm not done my question, because the question was, what is the pH of ammonia? And so now I'm going to embark upon the last step in this question, which is to use the fact that my value for x, my value that I found for x, is actually the same as my hydroxide ion concentration. So that 1.9 times 10 to the negative 3 is, when I go ahead and I look at what x is actually meaning here, and that's what it means. And so that's the moles per liter. That's going to allow me to find my pOH, okay, which is going to be the negative log of that hydroxide ion concentration, 1.9 times 10 to the negative 3. So when I go ahead and do that, I get a value for pOH that is 2.7 roughly. So 2.7 is a value that makes sense for a basic solution, and if we're talking about pOH. If you had done this as though you were finding the pH and you had an answer of 2.7, that's where you have to sort of rationalize and say, wait, if that's a pH of 2.7, how is this a solution that's a base? That doesn't make any sense. And so that's where I'm hoping you would go ahead and say, okay, well then I know that my pH I'm going to get by knowing that the pH plus the pOH is going to equal to 14. So my pH is going to be 14 minus that 2.7. which is going to give me a pH value of, I'm going to try to squeeze it in here, of 11.3, which of course makes sense for a base. Okay, so that is the next part of this lesson. I'm hoping that you understood that reasonably well and can progress with the homework before commencing the last part of this lesson, which will involve looking at polyprotic acids, as well as having to find Kb by looking at your Ka values.